things about statistics and just pure application of statistics to data. So I'm gonna do that in a second. About scaling and why scaling of data is important. So I'm gonna start with an assumption that we have some kind of model. So we're trying to predict an output variable. So say you're trying to predict the position of a person on the accelerator pedal. And so that's going to be your output variable. And you want to predict it based on, say, the speed of the vehicle and the brake pedal. Okay? So you have some variable x1, which is your speed, variable x2, which is your brake pedal position. And now, the range of these variables may affect your result. So say your speed may vary from 1 to, I don't know, 10,000 in value. So not actual speed, but just in value. Versus your angle of the brake might only vary from 1 to 1.5. So this variable will change in value in a very small range of only 0.5, while the change in the range of x1 is huge in comparison. So what will happen is, for example, your w1, the weight of this variable in your predictive model, might be very small because the x1 value is so large. Versus w2 here will be really large because you need to scale this up. So this, of course, if the y is scaled differently, these values would change. But the point is that the change in one weight variable might be very different or might be much larger than a change in the other. So why is that important? So let me draw this out. So assume you have your W1 here and W2 here. And here we have your mean squared error. So basically the metric used to fit your model to predict your accelerator position. So say W1 and W2 take on like this shape. So that means we're looking for some value of W1 and W2 in this space. And we're trying to optimize the mean squared error, and mean squared error is over the z-axis. And the point is we want to figure out a value of W1 and W2 that creates the minimal value here, right? So we want to have as little error as possible in our model. So usually, if W1 changes only a little bit versus W2 changes a whole lot, what we'll have is a shape like this that we're trying to optimize. That goes down, right? So it's basically this top portion here. Whereas if we have scale data, our W1 and W2 will be a perfect circle. So you guys familiar with gradient descent, right? So gradient descent basically means I pick some value here and I change the values along the line here in order to reach this minimal value. So when a shape is oblong like this, what happens is you start picking a value over here and you try to go a bit here to get closer to the middle. Then since the change here is so little, you actually start overshooting, right? You start continuously overshooting and jumping around until you might eventually hit this middle point. So it's very inefficient in terms of finding this optimal value. Whereas if you're in circle, you're actually going down along the shape and is much likely to find this minimal value much quicker. So another reason for wanting to scale data and wanting to have this circular shape is the learning rate. So say you have your starting point is somewhere over here on your shape. To get to the middle, you need a very small learning rate so that the jumps you make are super small and then you get to the middle. If you're starting over here, your initial guess for what the weights are. To get to the middle, the most optimal solution is to make really large jumps to get quicker to the middle. If you start somewhere here on the shape, it's somewhere in the middle, right? You need a different basically size of a jump. So the problem is, depending on where you start in this shape, your learning rate changes. So you can't just decide to use a middle one to be more efficient. You need to actually choose the slowest rate just to make sure that you never overshoot, or you are more likely basically to find this optimal point. So, and choosing the smaller rate becomes very inefficient, say if you start from here, because you're doing very tiny jumps and in order to get to the middle, and some algorithms will actually give up because it's taking too long to find this optimal. So they'll say, no, I can't train your model. I can't find that area. On a circle, on the other hand, no matter where you start, you can choose one learning rate and it'll be the same regardless of where you started in your space. So that way it's more predictable basically how long it'll take, and the fact that you'll actually be able to train your model. So gradient descent is often used in neural networks. So this is when you're fitting neural networks. A different example is clustering. Clustering is another point where scaling really matters. So say I have my x1 and x2, right? And I have a small variation here and a large variation here. So say my values fit something like this. A lot of clustering algorithms will weight both variables the same. So they say that the change or differences I see in x1 are they're equivalent to the differences I see in x2. And then it's going to say, oh, I see more difference, more variation in points in x2, and it's only going to use x2 then to create the clusters, right? Because it's much easier. But because of the difference in scale, it might be really ignoring any kind of variation, or not weighting as higher or anything, the variation in x1. So if there is something to cluster in x1, your clustering algorithms won't notice it. And this is also important for PCA, so principal component analysis. Principal component analysis is a dimensionality reduction technique, and it always creates your vectors along the line of most variation. So in this case, it will basically keep using x2 as to create the vectors, and will avoid or not pay attention to x1. Scaling the data will get rid of that factor. So basically you'll have similar scale. So if there is a variation in x1, so for example in vector scaling, you start noticing that some of the values here are slightly different from the values here, you will actually notice the different clusters, potentially. One last thing to note, so when we create the circles here, we use a standard deviation of 1. That's why we have a unit circle like this, and that's what we look for when we scale. And we look for a mean of 0. And the reason is we want to place our circle right around the origin, basically removing any numerical complexity. And making sure there's no errors happening due to the circle being, say, in a very large value area, where some programming languages might start adding or subtracting small numbers from large numbers and giving you basically unexpected results. And lastly, how do you scale? So say we have some value, so x1 was our speed, we'll take x1i, we'll subtract the mean, and divide over standard deviation. And that's exactly how we'll get scaled values for our variables. And then we can more reliably fit the model. That's all. Any questions? Very basic stuff, but basically an explanation for why we do something like that and why it's important. All right, thank you.